Welcome to our 8.4b lesson notes. In this lesson, we're going to talk about parent trig graphs, or the parent graphs of our trig functions. In particular, we're going to look at sine of theta, cosine theta, and tangent of theta. So kind of our three main sine, cosine, tangent. I wrote them up here in function notation using theta as my variable. This is theta, right? For some reason, mathematicians take a liking to certain Greek letters representing stuff, and theta is often used to mean an angle. So sine, cosine, tangent are all, dependent on the angle that you're looking at. So we say sine of theta. You could write this the same thing as saying y equals sine of x, but this just looks fancier, so I'm gonna write it like that. Okay, first thing we're gonna look at is graphing periodic functions. It's the same thing, but we're gonna graph y equals sine of x, okay? Remember, sine of x, if you look at our unit circle, so beautiful, for any given angle, so say we're looking at 30 degrees, here's 30 degrees right here, sine is defined to be, we look at where that angle, this terminal side of the angle, intersects the unit circle, and sine is this up or down value. This is sine of 30, and it's 1/2. The y coordinate is always up or down. So the sine function is asking, basically, as I walk around this circle, as I'm walking around, depending on what angle I'm at, how far above or below, if I'm right here, how far below the x-axis am I? That's sine. So sine is up or down. Whoops. Sine is up or down. So given that, since we're looking at up or down, we're looking at the y coordinates. I'm going to erase these, clean these up. So let's fill in our graph that we have over here. So we're going to be looking at our y coordinates. So first we're going to look at when x is pi force. So when we're looking at the angle pi force, here's the angle pi force right here on our unit circle. What's sine of pi force? Well, it's this value right here. Sine and cosine are actually equal at pi force because you're the same amount to the right and the same amount up or down right at that point. But that's going to be square root 2 over 2, which is about 0.71, if we wanted to approximate it with a decimal. It's about 0.71. That makes sense, because if we're thinking how far above are we, the highest we're ever going to be above x is right at this point, right, where we're exactly 1 above, the radius is 1. So everything in here, all of these y values should be less than 1, right? That's the most we'll ever get. Okay, pi halves. Oh, look, that's what we were just looking at. Here's the angle pi halves right here. This is pi halves. So we're looking at the y coordinate. So sine of pi halves is 1. That's a really important one to remember. We'll keep looking at this. Sine of 3 pi force. Here's 3 pi force right here. So we're 3/4 of the way around the top. Remember, 1/2 turn is 180 degrees. So our sine value is square root 2 over 2. Again, still positive because we're above the x-axis. So about 0.71. All right, at pi, here we go. We're looking at pi. Sine of pi, when we're sitting right here, we are on the x-axis, so we're 0 above or below. So sine of pi is 0. Okay, sine of 5 pi force, you can keep looking around, filling this in. This is negative square root 2, because when we're sitting at this point on our circle right here, we are below the x-axis, about 0.71 below it. And 3 pi over 2, oh, now we're exactly 1 below, so -1. 7 pi force, okay, we're back right here, kind of like a quarter of our way up the circle, so we're at negative square root 2 over 2, which is about negative 0.71. I should have put a negative right there, negative 0.71 for 5 pi force. And by the time we get back to 2 pi, we're sitting right where we started on the x-axis, so we're 0 above or below. So those are our values, and now we're going to graph them right here on this graph that they gave us. So let's look right here. At pi force, our value is 0.71, so we're about right there-ish, almost a quarter of the way up. At pi halves, we're at 1, okay? We could have done at 0, we start right here on the circle, right? And we should start at 0 also, so we could fill that dot in. 3 pi force, we're back at 0.71. Then back at 0, then we go to negative 0.71, negative 1.71, and then we're back to 0. Okay, and if we were to go over that process again, so we've walked all the way around our circle one time, if we decided to walk around again, the y values are going to stay the exact same, right? The up or down when we walk around again. So you can see how this is going to be a periodic function. And just every time we walk around the circle, this is going to repeat. So we could keep going. And it looks like the pattern is we start in the middle, and then we go up. So we go like up to the top and down. I don't know. Let me see. So we're going to go back to 0.71, positive 0.71, and then to 1. And then square root 2 over 2, back to 0. And then we would come down. So I'm going to highlight that one period. Here's one cycle. We get all the way back to the middle, and then it's going to repeat right after that. And I'm going to keep drawing it to the left too. So if I go to the left and I'm repeating it, or we could go to negative 2 pi and start, because we know it's going to take negative 2 pi. So we go up first, bam, 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 and then back to the middle and down as we go to the bottom of our unit circle. We go below the x-axis. Nice. All right, that looks pretty good. And it would keep going this way, like forever. So we could keep doing that. Bam, like that. Cool, so that is the graph of y equals sine of x. There are a couple of things that we wanted to point out right here, like the max value and the min value, and we're gonna write those in down here. So it says periodic functions are functions that repeat their values at regular intervals on periods. We talked about that last lesson. The period of a function is the length along the x-axis. So it's like how much time of one complete cycle of the graph. The amplitude, so here kind of our key, there's period and amplitude of a periodic graph is half the distance along the y-axis between the max and min values of the function. So I think of the amplitude as like if you find the middle line, so like for this graph we just drew right here, our middle line, we were kind of centered around 0, and then it wiggled up and above. It's like how much are we wiggling up or below the middle line. So let's fill in these things. First off, the period. So we said it took us 2 pi to walk all the way around, or you can see that we went from 0 to 2 pi. That's when it started repeating. We made it all the way back around. So our period for this is 2 pi. 2 pi. Okay, absolute max. So if we look at the highest value we ever achieve, the highest we ever are on the circle is right here at pi halves, right? And that's 1 above. And you can see that we hit that every time. We hit that multiple times every time we get to that top point. So this is the max value. If I could draw on that line, there's the max value, and that is 1. And we also have a min value. The lowest we ever get on the circle is right there at 3 pi halves. We're exactly 1 below the x-axis. So our absolute min is at -1. Okay, then we're going to look at a couple more things. First off, those absolute maxes, like I said, we keep repeating those. Like there's one right there. So we have one at pi halves, at 5 pi halves, and at -3 pi halves, right? So this is saying the absolute max value is 1, like that is how high it is. This is saying absolute max at x equals, so it's like where do these happen? What angle are these associated with? So the way we can write that, because there are an infinite number of them, right? It's every time we hit this top. So normally how we'll write that is we'll say, well, it happened at pi halves, right? Our max happened at pi halves, which was when we were very top. And then it's going to happen every time I walk all the way around again, either to the front or the left. So it's like plus, walking all the way around again is 2 pi. But we could do that we could add 4 pi, we could add 6 pi, we can get any number of 2 pi. So we'll say plus 2 pi n, and we'll let n represent, so n is going to be like the number of turns you're taking. So if we were standing right here, to get to this -3 pi halves, we would make n -1. Like we're saying, we're take 1 turn, like backwards, 1 whole turn backwards, and then we'll get -3 pi halves. If we wanted to do 5 full turns forward, then we'd do 2 pi times 5, and then we'd add 10 pi to the number, and that would get us where we are. Okay, we're going to do something similar for the absolute mins. So they happen in a different place. The mins happen right here on the bottom, so they're at the bottom of these valleys. And on our graph, that's associated with the lowest point we're ever at is right here, which happens at 3 pi halves. That's the min. That's the angle which gets us the min. So it happens at 3 pi halves. And then it's going to happen again anytime we make a full rotation, either forwards or backwards from that point. So we can write that the same way. So we just say a full rotation is 2 pi. And then we can go any number of full rotations. We could go backwards 52 times. We could go forward 7 times. So we'll just put an n right there. Cool. And maybe we should say, I guess n could be positive or negative, but if we want n to stay positive, we could say, like, we can go forward, or we could do, like, plus or minus 2 pi n if we wanted to. Plus or minus. And then it'd be like, oh, minus 2 pi times 5 would be backwards 5 times, or something like that. Okay, another place we want to look at that's important for us are the zeros, okay? So zeros meaning where does it hit 0? So we can see it hits 0. For the max and the min, it was only hitting a max and a min 1 time per cycle, but the 0, it's actually hitting twice per cycle, right? If we look at the cycle trapped right here in between 0 and 2 pi, it starts at the 0, and it hits 0 again in the middle, right? So how can we write down the pattern? So it hits at 0, pi, 2 pi, okay? I'm going to write these down. So it's 0, 0, at pi, at 2 pi. So it's like every time we take a half turn, basically it's any integer multiple of pi. So ... we could just write that as like plus or minus n pi. So it would happen at 5 pi, it would happen at negative 13 pi, any like full pi rotation. Okay, cool. Amplitude. So our amplitude, we're saying like how much wiggle room do we have? So look from the middle line, how far above and below do we wiggle? We wiggle 1 above and 1 below. So our amplitude is just 1. Okay. Our domain. So remember, domain is left to right. Okay. This goes like it's going to keep going to the left and keep going to the right forever. So our domain is negative infinity to infinity. We're allowed to put in any angle we want in there. Our range, however, remember range is bottom to top. It's kind of wondering like what possible outputs can we get. And from our circle, we can see the only possible numbers we're ever going to get are in between -1 and 1, right? We're only going to output numbers in between -1 and 1 when we shove them into this function sine. So our range, we can get -1 though. So I'll put a bracket, -1, that's possible. And we can get anything up until +1. And we can get +1, but nothing outside of that. So that's our range. Cool. So that is graphing sine of x. That's what sine of x looks like. It looks very similar to those Ferris wheel type questions, right? Because we're talking about how high up are you as you ride the Ferris wheel around. Dun, dun, dun. Okay, cool. Let's look at cosine of x. So this is going to be really similar, but remember on our unit circle, when we're looking at cosine, for any given angle, so say we're looking at 60 degrees, here's 60 degrees right there, we look at where it intersects the circle, and you can kind of draw a perpendicular triangle. Wherever we're looking, we're wondering how far to the right or the left of the y-axis are we, right? So we're wondering like how far to the right or the left are we? So right here, we are, the x-coordinate tells us left and right, so we are 1/2, so this is like 0.5. We're literally halfway across that circle, okay? So we're looking at how far to the right or left are we when we're looking at cosine of the y-axis. Okay, I'm going to erase this. And we'll fill in our graph. So at pi 4, so that's our first one. I kind of want 0 to be the first one though, right? When I'm right here, how far to the right am I? Well, I'm all the way, the furthest to the right I can be is 1. So maybe I'll add an extra column right there. When x equals 0 or theta equals 0, y equals cosine of 0 is 1. So we're all the way to the right. Okay, so at pi 4, here's pi 4. How far to the left or right are we? Well, we are ... square root 2 over 2, which is about 0.71. All right, at pi halves, here we are at pi halves. This is our angle pi halves. How far to the left or right of the y-axis are we? Well, we're right on it, so we're 0 to the left or right. So 0. 3 pi 4. By the time we get to 3 pi 4, we are back at being square root 2 of 2 away, but now we're to the left, so we're going to be negative square root 2 over 2, which is about negative 0.71. At pi, we are the furthest away from the y-axis we can be to the left, so cosine is -1. 5 pi 4 is down here, so we are negative square root 2 over 2, so we are to the left of the y-axis, square root 2 over 2. At 3 pi halves, we're straight down. So we're wondering how far left or right are we? Well, we're not at all. So cosine of 3 pi halves is 0. 7 pi fourths is right over here. We're back to the right of the y-axis now, so we're positive square root 2 over 2. This should have been a negative 0.7. I did that same thing on the sine one. Anyway, 2 pi. So back at 2 pi, we're back at the beginning. How far to the right are we? We are all the way to the right, positive 1. Cool. And then we're going to fill in here. So these are like the same numbers that we had before for sine, just a little bit offset almost. So at 0, we said we started at 1 because when we start on this side, we're as far away from the y-axis as we can get to the right. So positive 1. And then we're going to, at pi fourths, we're going to have the point pi fourths 0.71. So then we start getting closer to the y-axis. At pi halves, we are at the y-axis. By 3 pi fourths, we're to the left of the y-axis, square root 2 over 2. And by pi, we're all the way to the left of the unit circle, as far left as we can go, so negative 1. Then we start coming back towards the y-axis. We're at negative 0.71. We hit the y-axis at 3 pi halves, right here. And then we go back positive 0.71 to the right. And then we meet up where we first started, all the way to the right of our unit circle at positive 1. So that's one entire cycle of cosine. So we start at positive 1, and then we get closer to the y-axis, hit the y-axis, start going to the left, all the way to the left of the circle, to the bottom, we get back to the y-axis, and then back to the top. So that's one whole cycle. I'm going to show that by just highlighting that. Notice our period here, it goes from 0 to 2 pi again, and that makes sense because it takes 2 pi to walk all the way around the circle. So our period, I'm just going to write that in right now. We're on at 2 pi. Period is 2 pi. All right, if I were to walk around the circle again, now I'm right back where I started. If I walked around again, my distance to the y-axis would change the exact same, so we can repeat this. Now this one starts at the top and goes down, hits the middle, goes down, hits the bottom, and comes back up. So that's what it would look like if it kept going that way. If I were to walk around backwards, well, this is what it would look like. Just going to finish this up. Negative 0.71 back here, to the middle, up, back down, whoo, all the way back down to the bottom. Oops, that got a little crazy. It's okay. Cool. Okay, so you can see each of those like repeats on our cycle. There's another cycle that goes from negative 2 pi to 0. Nice. And then we have these half cycles off the side here. Okay, absolute max. So the absolute max, once again, the furthest we ever are from the y-axis is positive 1. So that's absolute max is happening right here. But where does it happen? So the absolute max is 1. Where does it happen? Well, we actually started there at 0. And then we hit it every time we make it like all the way around the circle, right? So 0, 2 pi, negative 2 pi, we're going to hit it again at 4 pi. So it's like 0 plus or minus 2 pi n. Seems a little bit strange, but we start there, and then every time we do a full circle, which we can go forward would be like plus some number. So if I wanted to go forward 10 times, I would do plus 2 pi times 10. If I wanted to go backwards, then I'd go minus 2 pi times 3. Backwards 3 full turns. Remember, 2 pi is like a full turn. Okay, absolute min, the furthest away from the y-axis that we get to the left is all the way over at pi, and that's negative 1. So our absolute min is at negative 1. Like I just said, that happened at pi. I gave it away. It happened at pi. Here it is. And then it happens again every time we do a full circle. So it's like pi, 3 pi, negative pi. It's like all the odd pi's for this one. So we're going to do pi plus or minus 2 pi n. So we can go forward or back full circles. That pi looks significantly different than how I did all my other pi's, and that bothers me, but I'm going to leave it. Okay, what's our amplitude? Once again, our amplitude, we look at the midline. Here's our midline is 0. How far do we waver from the midline up and down? Well, just 1. We're wiggling a max of 1 up and 1 down. So amplitude is 1. I forgot to do the zeros, so we should go back and do the zeros. Zeros happen, let's see. I'm going to look back at our like original period. So 0 happened at pi halves. That's when we were right on the y-axis, and at 3 pi halves. So it's like every half turn starting at pi halves. So we're going to do pi halves for zeros. And a half turn is just 180 degrees is just pi. So this is pi halves plus or minus, but any number of half terms. So we can do like plus or minus pi n. It's like pi halves, 3 pi halves. Anyway. Okay, we got our amplitude. Domain, this is going to the left and the right forever. We're allowed to go any angle on the unit circle. So our domain is negative infinity to positive infinity. For domain and range, we always go like least to greatest when we write it like this. And then our range, so our outputs, like how far up or down, the smallest we ever get is -1, and the biggest we ever get is 1. So our range is -1 to 1. Notice I'm using those closed brackets because we do actually hit -1 at some point, and we do actually hit 1 at some point. Awesome, that's cosine. Sounds good. So it looks remarkably like the sine function, just sine function would have started like right here, right? Sine, or whoops, I got off by 1 there. Sine starts in the middle, whereas cosine starts at the top. Okay. All right. Now we're going to look at tangent. So tangent is going to be strange, okay? Remember, tangent are, if you're looking at the unit circle, you can calculate tangent as the y value over the x value. Because remember, tangent, so like tangent of theta is sine of theta over cosine of theta, okay? Yeah, tangent is sine over cosine. So sine is the y value, and cosine is the x value. So we can just do y divided by x to get this. So we're going to look at pi force. So here's pi force right here. So we look at y over x. So it's square root 2 over 2 divided by square root 2 over 2. So it's something divided by itself, right? Square root 2 over 2 divided by square root 2 over 2. That's just a fancy 1 if you divide something by itself. So tangent at pi force is 1. Remember, you can think of tangent as kind of a ratio of sine to cosine. And when sine and cosine are exactly the same, tangent will be 1. Okay, pi halves. So here we are at pi halves. We have y, which is 1 over 0. That seems bad. 1 over 0. That's a bad thing. We can't divide by 0. This is undefined. That's not great, but, you know, whatever. What happened to tangent as it got really close there? That's something we could think about, though. Anyway, 1 over 0. 3 pi force, okay, if I look at 3 pi force, here I am, 3/4 away around the top. I have square root 2 over 2, that's the y, over negative square root 2 over 2. So square root 2 over 2 over negative square root 2 over 2, that's almost like a fancy 1, but with 1 negative. So this is -1. All right, at pi, here we are at pi, y over x, that's 0 divided by -1. That's okay. We can take 0 and divide it by things. That's just 0. Okay. 5 pi force. Here we are. 5 pi force. So I have negative square root 2 divided by negative square root 2. That's something divided by the exact same thing. That's a positive 1. And then 3 pi halves right here. Uh-oh, the bad thing's going to happen. We have -1 divided by 0. It's undefined. And then we have 7 pi force, which is a negative square root 2 negative square root 2 over 2 divided by square root 2 over 2, so that is -1. And then lastly, we have 2 pi. We get 0 divided by 1, which is just 0. Okay, this is a little bit strange, but let me show you what this is. So we're going to plot what we can do, and I'll show you how to connect the dots. It's really kind of strange. Okay, I'm going to graph it in blue. Okay, pi force. So at pi force, we have the point 1. So at pi force, we are up 1. Great. That's awesome. At pi halves, we are undefined. So there's not a point at pi halves. It's kind of strange, right? Okay. What if we had looked at negative pi force? Sorry, negative pi force. Negative pi force on our graph, that means we start at 0 and we go backwards, like a quarter, like an eighth of a turn, I guess, of the whole thing. So negative pi force is the same as 7 pi force. And at 7 pi force, we had -1. So negative pi force is actually going to be not this point right here. Negative pi force would be at -1. But then at negative pi halves, we'll be back to being undefined. So where it is undefined, we're actually going to have vertical asymptotes. So we've seen vertical asymptotes before. Where it is undefined, so that's at pi halves, it's undefined. I'm going to do like we saw these with logarithms, right? We have vertical asymptotes. Every time we land on this y-axis, we have y over x, and the x coordinate is 0. So that's going to be at every like multiple of pi halves or 3 pi halves, right? Like every quarter turn. So it'll happen at pi halves. It'll happen at, you can also look and say like, oh, that was 1, 2, 3, 4 in between. So 1, 2, 3, 4. It's going to happen at 3 pi halves. It's going to happen again at 5 pi halves. It'll happen again at negative 3 pi halves and negative 5 pi halves. Okay, and in between there, at 0, we didn't fill in a point here at 0. At 0, we're right here. We have 0 divided by 1. That'd be 0. Okay, this is what tangent looks like. Are you ready? You might say like, oh, look, it's just like that. Well, no, it's not. It actually goes really, really close to that one right there, and then comes in. It almost looks like a cubic function. So it comes in here. I'm going to try and draw it nicely. And then goes up like this. And then it repeats because it's periodic. So then over here, it's going to start really close to the vertical asymptote. You're going to hit negative 1, 0, and 1. But it's going to come in and do like a squiggly like this. And we'll have negative 1, 0, and 1. And it'll come in and do a squiggly. Just like that. And this one will start here. It'll go up. So it's super, super weird. It just repeats like this. Oops, not there. Negative 1, 0, 1. Okay, and how do we know that it's going to keep getting, like, how do we know that it's going to do this? Why do we know that it's going to, like, get a lot closer? Well, that's kind of an interesting question. It's actually more of a calculus type question. So we're looking, like, zoom up on your unit circle, okay? And as we're coming in this way, remember, tangent is comparing sine to cosine, right? So we keep getting these smaller and smaller triangles. So somewhere up here, I have like a triangle that looks like this, right? Whoa, looks better than that, right? And this is sine, and this is cosine, right? And then I get an even smaller triangle, like it's going to be like this. Oh my gosh, that was really bad. It's going to be up here like this. Bam, bam. Sine, cosine, right? So we're comparing sine of theta over cosine of theta, and cosine of theta is getting really, really, really tiny. Like as we get closer, we're getting closer and closer to this y-axis, so cosine is becoming smaller and sine is becoming big. So we're getting like big over small, basically. And if you think of big over small, like what about like 1 million over 1? That's kind of big over small. That's a really big number. So as we look, as we're getting close to pi halves on our graph, here's pi halves, we're getting this where it's just getting big, 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 really, really big. But when we actually get to 0 on the bottom, we can't actually like deal with that. We can't deal with that. 0 on the bottom. And so that's how we get that vertical asymptote. Same thing kind of happens if you look at the triangles that happen as we're like getting close to 0. Like if you look at the triangles that would fill in here. So like at pick a different color. How about bright green? At pi 6 we have this triangle, right? And this is sine going up, and this is cosine side to side, okay? And that's fine. Apparently the ratio there is 1/2 over square root 3 over 2. Remember, 1/2 divided by square root 3 over 2. If we divide, we got to flip and multiply, right? So this becomes 1/2 times 2 over square root 3. So I changed it to times and then flip the bottom one, and then we multiply straight across. So I just have 2 over 2 square root 3. But then I can, this 2 over 2 is like a fancy 1, so it's like 1 over square root 3. If you want to be really good and rationalize the denominator, then you'll get square root 3 over 3. But sometimes we don't really worry about that. Anyway, so it's like 1 over square root 3. Okay, But then as we get close, like say we look at a point right here, a really, really small angle right here, then the triangle that we would draw is just like this, right? And cosine is going across, and cosine is getting really big, but sine is getting really small as we get closer. Like we're getting closer, we're getting smaller, but further out. And we're looking at sine over cosine. That's what tangent is. Whoops. I should write that better. So sine theta, cosine theta. This angle is all the same. So we're just looking at the small angle. Sine is getting small, very small, over like a really big boy. I hope someone's watching this and that you laugh if you made it this far. Okay. And if you think about that, it's like having like 1 over like 1 million. That's like small over big, right? And that 1 over 1 million is basically 0. Like that's really small, right? Eventually we get to the point where we are at the, we're up or down nothing all the way over, and so we get 0 over 1 eventually, and that's okay. So really maybe we should have looked at the bottom, that as we I guess really what we wanted to be interested in is why, the question we want to answer is why does it go like up on this side of the vertical asymptote, but down on this side of the vertical asymptote? Like why is it going to positive infinity here, and it goes to negative infinity right here? That's really what we want to know, right? And these, we're looking at the angles that are just barely bigger than pi halves, right? So the angles that are just barely bigger than pi halves are the triangles, or the, like this angle right here would be just barely bigger than pi halves, just further than pi halves. If we look at that triangle, looks like this, right? The same kind of thing is happening, except now we're looking at sine. Sine is still positive because we're up, but cosine, now we're to the left, so cosine is small. And as we get closer, it's like we're looking at sine over cosine, and we're looking at like positive big over negative small, which now becomes like, we think of that as like 1 million over negative 1, which is still like basically infinity. Like that's gonna get really big, but now negative. It's like negative really, really big. So that's why as we come in this way, as we look from the like left of our angles, as our angles, like when our angles are smaller, but they're approaching it, they're almost at the point, it's positive infinity. But as we just barely pass it, now cosine is negative. So now it's negative infinity starting at that point. So it's undefined, it's positive infinity, undefined, right at pi halves, and then negative infinity. And that's how we get this weird pattern. Anyway, I'll stop ranting about that, but I hope that made some sense. So let's look at here. The period. So this one repeats, it doesn't take 2 pi. One period happens just in between these two vertical asymptotes. And that is just from negative pi halves to pi halves. So the period here is actually just a pi, 1 pi. Absolute max, well, there isn't, because it goes up to infinity. So I'm going to say none, or does not exist, absolute max. So, there aren't any, so we can't say where they are. Same with the min, it goes down to infinity. So there's not, like, we can't pick one number that's the smallest number, because it keeps getting smaller always. Okay, zeros, it does hit zeros right in the middle of each one of these periods. So that's at 0, at pi, at 2 pi. So it looks to me like it's 0 plus or minus any number of half rotations, like any number of pi's. Okay, amplitude. Amplitude's kind of strange because we're wondering, like, I guess the midline, we could say it's at 0, but it's kind of weird to say the midline's at 0 because it goes up to infinity and bottom to infinity, and like infinities is weird. So we don't really talk about the amplitude. Instead, we could talk about a vertical stretch. I'm gonna write that smaller. Instead, we could talk about a vertical stretch. And when we talk about the vertical stretch, we're kind of looking at these. We have these like 3 anchor points in the middle. And we're talking about like how far down and up are these 2 anchor points. So these are like stretch 1, right? Like this anchor point is up 1, this anchor point is down 1. And we could do weird things to the tangent function to make it stretched out a little bit more. Like if we want it to be down 2 and up 2, we could do that. But our parent graph, just tangent of x, or tangent of theta has a vertical stretch of 1, meaning those anchor points are sitting like this, and it's like down 1 and up 1. That's kind of a weird drawing, but whatever. Okay, domain. So the domain now is kind of strange. If we look left to right, it keeps going left to right forever, but it has these breaks, right? It has breaks every pi. This number is not in the domain. We don't have, where those vertical asymptotes are, those are not in the domain. So we have to, do breaks. So one thing we could say is the domain, you can either say, well, this is what we'll normally say. We'll basically say everything except for this. And so we can say, like, the domain is, if we're talking about theta, or you can make it x, doesn't matter, whatever you want to call it. Maybe I'll call it x because we had an x right there. So x is not equal to, so we're going to say things that aren't in the domain, and it implies, the rest of the stuff is in the domain. So these breaks happened at pi halves, at 3 pi halves, at 5 pi halves, at negative 3 pi halves. So I think that's happening at pi halves, plus or minus any number of half turns. Because it happened at the top of our circle and the bottom of our circle. So we had to get, this gets us to the top of the circle, and then this is like any number of half turns from there to go to the bottom or back to the top. Half turns. Because pi is only 180 degrees, half turn. There's a song about that. I think 180 degrees. Crazy. Okay. And the range. So now the range, we're wondering top to bottom, where are all the possible numbers we can spit out from top to bottom? Well, every single time we look at one of these cycles, we actually spit out every number all the way down to negative infinity, all the way up to positive infinity. So the range now is negative infinity to positive infinity. Okay, and asymptotes. We have asymptotes. Asymptotes are the same place where we had this domain breaks, right? So this is actually kind of asking the same thing. Where is the domain not, and where are the asymptotes? So x not equal to pi halves plus or minus pi n. One thing to notice right here, where these asymptotes are, you could think about this for yourself a little bit, but look at where these asymptotes are. Pi halves plus or minus pi n. Oh, I don't want that to be a not equal to right there. The asymptotes are at that point. We said not equal to here because we were saying these are not in the domain because they are asymptotes. The asymptotes are at these points, so we want that to be an equal sign. Pi halves plus or minus pi n, I've seen that before. That was where the zeros of cosine were. And I wonder why those might be the same. It might have something to do with the fact that tangent of theta is sine of theta over cosine theta, and it would be bad if cosine theta equaled 0 because we can't divide by 0. But I don't know. You think about it for yourself. Okay, I think I'm going to pause this video and make that a part 1 and then make a part 2 video because I've probably been talking for an hour.